Welcome to our Great Minds program. Today we have a spectacular great mind, Angela Olinto, professor at that place in Chicago, University of Chicago, in the astronomy and astrophysics department. She's a distinguished survivor of being a postdoc at Fermilab and a good friend, and she's her bio, if you like, or the is in this little pamphlet, so I won't read it to you, but she's really a spectacular contributor to our astrophysics and particle astrophysics. That's a new word, right? Particle astrophysics phenomenon. And today she's here to talk about chasing cosmic bullets, the Pierre Auger experiment. Angela?
Thank you very much. I think, let's see. Can you hear me here? It's better here, right? Yeah, it is better. Okay, so let's see if I can do three things. Three gadgets. All right, so you got my title and you know what my name is. Let's see, the next thing is what is the Pierre Auger experiment about? So first let me start with cosmic bullets. So here is what I mean by cosmic bullet. What you will see is downtown Chicago. So you can recognize here the park, Grant Park, and the pier, and Adler Planetarium. And what you will see is a particle that I call cosmic bullet, which is could be a proton or an iron nucleus, for example, that is hitting the upper atmosphere, and it has so much energy that it becomes hundreds of billions of particles by the time we get to the ground. So this is what we call an air shower, and these particles, the origin of these is my main concern. Okay? So this happens from time to time. It's not super often, but from time to time we get a whole downtown lit up by these particles. So nature's accelerator is my topic. What makes these particles, these cosmic bullets, reach such high energies? And also, what can they tell us about interactions? How can we use them, like people at Fermilab use them, to understand interactions at very high energies? So the questions we would like to answer are, where do they come from? How do they get accelerated? What do they tell us about the forces of nature? And the first two is in the astrophysics realm, while the third one is really a particle physics question. Now, this is 2010, so this is an old slide. But last year, we were celebrating 400 years since Galileo used a telescope to understand the sky. And here's in Spanish, one of these posters. I've seen this everywhere last year. It was really kind of fun to be in this small town in Portugal, for example, and to see one of these posters. So the whole planet really got into astronomy for a year. And it was really a special year because in 1609, we had the telescope we pointed to the sky by Galileo, but also we had Astronomia Nova from Kepler. Now, after 400 years, the photon is really the favorite particle of astronomers, but not only the photon that Galileo looked at, which is the one we are used to, the visible photons, which are over here, but we can observe the universe with photons of much longer wavelength, or very low energy photons, we would say, a radio, for example, frequency type. Or you can go to very high energies, all the way to gamma rays, and look at the universe that way. And by looking at the universe with all these different particles, with all these different energy photons, these are all the same particle but different frequencies. And the wavelengths are given here by analogy. So you have, in meters, 1 meter microwave is a human scale, and you have protozoans here, molecules, atoms, and atomic nuclei. So, this kinds of photons here, the ones we call gamma rays, are really very high energy. They do reach into atomic nuclei. They get produced by atomic processes, but all this range can be seen in the universe. And we have been used in astronomy to use these kinds of eyes. So optical eyes are what Galileo began with, and here are some examples. This is the longest refractor, the Yerkes Observatory, that I hope you have a chance to visit. It's in Wisconsin, not too far from here. You have the Hubble Space Telescope that I'm sure you can visit, at least in the web, and see beautiful images. It's really a wonderful achievement in terms of optical astronomy. And there is the Keck telescope here, which are twin telescopes, and the Magellan telescopes in Chile and in Hawaii. And it's nice to have these kinds of capabilities on the ground and in the two halves of the hemisphere, in the southern hemisphere and in the northern hemisphere, to be able to actually probe the whole sky in optical wavelengths. Let's go and look at the longest wavelengths, the lowest energy photons, radio photons. These are what, for example, Arecibo observes, and here is for scale, a car. So you can imagine this is a really, really large dish, and that is designed to see this very low energy type radiation, which is radio radiation. And at the other end, we can look at the gamma rays. And gamma rays, there are two ways that we're looking at right now. The Fermi Space Gamma Ray Telescope is a recent development. We had it launched in the last year and a half. It has already given beautiful data. I'll show you an image from Fermi. This is if gamma rays don't make it to the ground, so you have to fly space observatories to see them at 300 GeV. But when you get to very high energies in gamma rays, around a TeV, you can actually use telescopes on the ground by having imaging of the shower. So the same image I showed you of a cosmic ray making a shower over Chicago, a gamma ray can do that too, and these telescopes, the MAGIC, HASS, and VERITAS, are designed to look at that. So, at the other end. And the kind of things we would like to see are things like this, which if the room was very dark, you would see a beautiful image. You can see a comet, which is sort of what the old astronomers were after. And they classified little clouds like these to get out of their way in finding comets. But to us, these little clouds are much more interesting. This is our own galaxy, the Milky Way, and here are the small and the large Magellanic clouds that if you go to the southern hemisphere, you would find them. It's actually beautiful. Where we are in the Auger Observatory, we see these very often, and it's pretty amazing that they look like clouds and they just don't move. They move with the sky as opposed to with the wind. This is images of the Milky Way also, but in different frequencies from the optical distance, microwaves and the infrared. And here is one of these Fermi images that I just mentioned. So this is the image of the sky at the highest energies. And what you can see is our galaxy for sure. So the galaxy has these high energy events happening. And most of this emission is probably the cosmic rays in our galaxy making pions. There's a lot of dust and gases and molecular clouds in the galaxy plane, and there are these cosmic rays which are high energy particles, and they interact and they produce some gamma rays. Also, you can see that there are these point sources all over. There's some of them which are pulsars, there's some which are extragalactic, other galaxies that are very luminous. So it's a very interesting part of the sky. But then there's also the part of the universe that I hope you've heard about, which is the surprising type, which is it's not actually seen by these photons directly. And there are two kinds of universes that we observe that are not done through the typical looking at photons with telescopes type. One is the dark universe, which you've probably heard about. If you don't, you will during your stay here. One is the dark matter and the dark energy. These are components of the universe that are actually the dominant. Dark energy is the dominant component of the universe, and dark matter is the dominant matter component in the universe. And neither of these we can see directly. We see them indirectly through the fact that they, if the laws of physics are the same as we have tested it so far to be true, they show that the presence of dark matter in halos of galaxies and the presence of the dark energy through the acceleration of the universe. Then there is another type of study of the universe that we can do with using particles, and cosmic rays is what I'll focus on today. But another way that we are hoping very soon to be able to use is to use neutrinos to look at the universe. Neutrinos have something in common with the photons that I showed you before, the traditional element in astronomy, because they have no charge. So neutrinos are very nice as ways of doing astronomy. The problem with neutrinos is that they're very hard to detect. So it's very tough to catch one of them, but if we can catch them, we can really see a very interesting image of the universe. Cosmic rays are easy to catch by comparison, but they are charged, so most of the time they're not good for astronomy because they don't point back to where they came from, so it's hard to do astronomy that way. I'll go more into that. But these are what we use particle detectors, just like people at Fermilab and other particle accelerators. It's similar idea to look at the way the particles interact when they hit the atmosphere. It's a much bigger detector in a sense, but it's made with simpler technology. So let's go back to the beginning of last century when this whole story began about cosmic rays. So cosmic rays in the 1910s became very fashionable to try to understand what they were. What they were at the time were basically when you put some charge in, say, electrostat, you would see it discharge even if it were in vacuum. So there was something that was coming in, an ionizing radiation that would make charge go away. And this fellow here, the Jesuit priest Wolf, he went up the Eiffel Tower and he thought that actually if this radiation was coming from the ground, by the time he got to the top, it would be much lower. And it was a little bit lower, but not as low as he expected. So he thought there might be another component. And then Victor Hess really showed what's going on by going up in a balloon up to 5,300 meters. So very courageous guy. He did it during the day and at night, and without oxygen. Pretty good mountain climber. And he found that the rate was actually increasing. So the amount of cosmic rays, the amount of ionizing radiation was increasing as a function of altitude. It sort of decreases a little bit and then it increases quite a bit. So the majority of these ionizing particles that were coming through in their detectors is actually coming from above, not from below. So here is a little image to keep track. It's kind of too, can you make it darker? There's the other way. No, I guess I can make it lighter. Because we'll see a lot of dark videos. So in this one, what you should be able to see especially if we can do, that's better, right? Okay, so we can see, lots and lots of cosmic rays hitting the Earth. And from time to time, very rarely, you see an ultra-high energy cosmic ray. These are the ones that make this very, very long, extensive air shower. But there's all the time a lot more. For every one of these, there's tons more of those which are hitting the Earth constantly. So the one nice thing that you can think of about cosmic rays is if you go to the Arctic Circle, for example, and you see the Northern Lights, you will remember that I talked about it, I hope. And basically what you're seeing is cosmic rays which are trapped in the Van Allen belt, kind of being smooshed around by the magnetic field of the sun interacting with those of the Earth. So here's an image of the Earth, and the Earth has a magnetic field which keeps the low energy cosmic rays from going down all the way. Depending on where you are on the Earth, it's more or less beamed, this sort of containment bottles. If you are very high energy cosmic rays, you can go right in. But if you're low energy ones, you can live in these sort of belts around the Earth. And from time to time, depending on the interaction between the Earth's magnetic field and the solar one, you get these beautiful northern lights. Oops, I can't do that, right? So my topic is really for the highest energy cosmic rays. And the highest energy cosmic rays were only discovered in 1937 when Pierre Auger, who is a French physicist and a pioneer in this field, discovered that cosmic rays can actually reach the Earth. Sorry about the spelling. I had all this stuff yesterday in Spanish, and I tried to move it very quickly to English, but didn't do a spell check. Okay, so this is Earth. It's not Earth in Spanish. It's Earth misspelled. That the cosmic rays he found reached 10 to the 15 electron volts. So how did he do that? What he did was he used, Geiger counters, which I hope you're all familiar with. Let me get my hand out of the way. And what he found is that events were hitting Geiger counters separated by some distance at roughly the same time. So there was coincidence events, and as you moved further and further these detectors from each other, you still would find coincidence events above what you expect from the normal rate. So if you have a rate of cosmic ray detection, you expect from time to time 2 detectors to be hit at the same time. But if that's happening a lot, that might be for some other reason. Okay. So let's make a little thought experiment, which is that each one of us have a cell phone, I imagine. If you're the one in the room that doesn't have one, let me know. That must be a rarity these days. And let's assume that these cell phones are actually particle detectors, cosmic ray detectors. So if we keep them around like this, they will be clicking at about 1 event per second. Okay? But from time to time, you could have all the ones in this room be clicked at the same exact, say, hundreds of nanoseconds. Okay? Okay, so all the cell phones will blip at the same exact time, and time in that sense is hundreds of nanoseconds. Imagine if all the cell phones of Chicago blip at the exact same time also. And again, same time here is within 100 nanoseconds. That has to be a weird thing. Okay, the probability of that happening by chance is zilch. So what he discovered by noticing this coincidence is that one single particle generated the whole shower that triggered all these blips to happen simultaneously. Okay, obviously they're not exactly at the precision of simultaneous depends on your measurement of time. But basically, one particle, as I showed you in the video, hits the upper atmosphere, makes a shower, and most of the power, and they are all moving at the speed of light, so they all hit the ground within that time. And if there's an angle between, the direction that it came in, it will have some things hit a little earlier than others, but all within the speed of light, the time crossing given the speed of light of downtown Chicago. Okay, so that's the time scale for simultaneity. So what he discovered was that particles were coming in, and at the time, the distance he had gave him 10 to the 15 electron volts for the energy of these particles that were triggering showers. And now we know a lot more about them because we've been able to look at them with balloons, with satellites, and with ground detectors, a whole range of different detectors, even airplanes. And what you know is that there's a lot of low energy cosmic rays hitting, and from time to time you have higher energy ones, which are less frequent, but when they happen, they trigger a very large air shower. And this is just the beginning of it. So a proton comes in, hits a particle of a molecule in the atmosphere, and makes pions, and they make electrons and positrons and photons and muons and so forth. So you end up with a large electromagnetic type of cascade, hundreds of billions of these, and also of muons, because the pions tend to decay too fast, and a little bit of a core with the hadrons. So it looks like this, a real core of shower and then all these other particles, and they're mostly going down, but some can go sideways. So there is a thickness to your shower, and this is what we tried to observe. So let's look at what we can learn, but let me go back and talk about the whole history of learning of all these three questions. Let's focus on the last one first. What do they tell us about the forces of nature? So I'm sure you know that this is what all of our daily experience is about, is up, down, quarks, and electrons. Cosmic rays were responsible for making us include the strange quark and the muons here. So the birth of particle physics and astroparticle physics dates back to the 30s when cosmic rays were used as our accelerators, and people put detectors and tried to see what was coming from these high energy particles. And what we found were positrons, anti-electrons, muons, which are heavier versions of the electron, then the pions, which are a mixture of up and down quarks. One is anti-quark and the other would be the quark, so that they have no baryon number like the protons and the neutrons would, so these things are called mesons. Kaons that are similar to pions are mesons also, but they have this strange quark, so they have this new quark here. This translation is a current translation. When they were measured, they didn't know about strange quarks, but they did call these things strange particles. The lambda is the up, down, and strange quark. We have the cascade and then sigma. And this is the history, and in '53, we had a split between trying to understand particles using cosmic rays and trying to understand the origin of cosmic rays, which is an astrophysical question. So of those three questions that I was referring to, they used to be all played together, and now we sort of split. Well, the astrophysicists try to understand cosmic rays at their origin, and here is a radio map of the cosmic ray effect in the galaxy. And here is what we know and love here at Fermilab, the particle accelerator, which is a much better way to study particle physics because you can actually control where the particle is going to hit your detector as opposed to be catching them as they fall. So let me just remind you a little bit how interesting these discoveries were and what we know today. So here is a bigger image of Fermilab, and this was as far as science results, the highest energy so far, at around the TeV. So the TeV is the tevatron, the name for the tevatron, and the TeV, I wrote it on the board, is actually 10 to the 12 electron volts. 10 TeV, which is the LHC, will be 10 to the 13 electron volts. Okay? So here's the next step, the LHC, the Large Hadron Collider at CERN, and it will have this huge circumference here of 27 kilometers, and it will reach 7 TeV per particle, so the collisions will be 14 TeV when they find each other. And the whole goal is to understand, for example, is the Higgs part of this story, right? So the particle universe that was built by people like Leon here in the room is this beautiful set called the Standard Model of Particle Physics, and there are pieces missing, for example, like the Higgs. So you have the quarks, which are the matter particles, the leptons, which are either versions of the electron or the neutrinos, and then we have the interaction particles like the photons, the gluons, the Z and the W bosons, and we're hoping to get the Higgs soon. So let me just remind you very quickly that this is certainly something you all seen many times, at least I saw them in many, many rooms today. So this is the state of knowledge 100 years ago or so. And then we zoomed in, we were able to zoom into, for example, the molecule of water, all the way to understanding the quark components inside the atom of hydrogen, which is the protons. Now, if we took the oxygen atom or any other atom, we would have two different combinations, the neutrons and the protons in the middle, but they're all done with the up and down quark, right? So we simplified 100 plus elements over here into 3 particles, which is beautiful. Then, we had 2 extra copies that nobody ordered that also seemed to find that were not necessarily expected. So things that were simple became a little more complicated. Who ordered these? And now we went, from 100 plus. We're still winning. We have 12, and we're hoping to find the Higgs. But it's still very unclear how the structure of particle interactions are set up this way, and why do we have 3 copies, and what gives different masses to these different particles. So what is this hierarchy about? So these are questions that we're trying to understand, and the higher the energies, the easier it will be, because, for example, the Higgs will show up hopefully at the LHC. And as you go higher and higher energies, you might discover some unification properties of these particles, some sort of higher order group that might be the birth of all these different low energy version of nature. So what I wanted to show you, just to compare, is that we're talking about 10 to the 20 electron volts instead of 10 to the 13, so it's 7 orders of magnitude higher, so it's a little bit expensive to build such an accelerator. So let me just remind you what an electron volt means. So a TeV is what we reach at Fermilab, and 1 TeV, T here is 10 to the 12, and an electron volt is what an electron gets if it has a voltage of 1 volt. So to get to 10 to the 12, you would need, if you only had these batteries, about 1,000 times their circumference to do the job. But obviously, we have much better than this battery at Fermilab, which is, for example, what you see here with these magnets in the tevatron. So you get interesting technology to be able to reach these kinds of energies. And with CERN, we get a little even bigger circle, so you have to do this trade-off between the size of your accelerator, the circumference, versus the amount of voltage you can actually achieve within a given distance. So in the case of CERN, the LHC will be in what's called the lap tunnel, which was the previous E plus E minus collider, and the circumference is 27 kilometers or 17 miles, and it's really down underground at about 100 meters or so. And here is Switzerland and France, and the border sort of crisscrosses the accelerator many times, so it's quite international in that sense. They do speak French on both sides, though, that helps. Now, this is part of the story, right? So you have the accelerator, which is what gives you this high energy, but then you have these yellow things, which is where the fun stuff happens, when the accelerator actually gets 2 bunches of particles to hit each other, and then you have to measure them. Now for that, we have amazing sophisticated detectors, which started with very simple ones. So here's a cloud chamber, and here's a bubble chamber. And basically you have some sort of medium where the particles traverse, and you might want to use some magnets to make, for example, charged particles turn around. So if you have a high charge, you turn around. If you have the similar charge but higher energy, you turn with a smaller rotation here, smaller, larger radius, smaller curvature. And if you have no charge, it goes right straight. And so this is an old image that people actually used to read by eye, which is unbelievable. And nowadays, that would be impossible. Here is one such detector, the CMS. Here's a person size, and this is the detector. It's very impressive. If you have a chance to visit, I suggest you do. I know at least one of you has been there. And you know, here's, they were built, in this case, up like we build these little boats inside bottles by bringing pieces down. Very scary. And these interaction regions will have different goals. CMS and Atlas are somewhat similar in their goals, and then there's LHCb, which is for B physics, and ALICE, which is over here, that will do heavy ion. So the LHC will definitely be the big show in particle physics. I hope it will discover the Higgs. This is what everybody expects will happen. It might address, you know, the 3 generations issue with that kind of discovery. It could also, hopefully, do the dark matter particle puzzle. What is the dark matter? Is it really a particle? Is it a supersymmetric particle? We might actually see it at the LHC. And then there is this sort of high risk, high glory. If we actually see extra dimensions, that would be quite interesting. So these are some of the goals of building such a beautiful machine. Now, in the astrophysics side, so this is sort of what happened since '53 in the particle physics end. And astrophysically, we've had a lot of progress also. Now, just to remind you what I said before, photons are the favorite particle for astronomers because they point back. They follow geodesics, okay? They follow the straightest possible lines. And instead of just saying a straight line, I use geodesics because some of you know about relativity. And general relativity makes geodesics really what we call straight lines because space might be curved and the geodesics is the straightest possible line given a curved space. And cosmic rays are, for example, a proton, a nucleus of the hydrogen, and it will have a charge, plus 1, and given a magnetic field, it will rotate around the magnetic field line, so it will be deflected. So if there are magnetic fields out there, we shouldn't be able to do very good astronomy pointing with protons. And sure enough, there are lots of magnetic fields out there. This is a galaxy, and this is a polarization map showing the polarization to the magnetic field of a galaxy, and that seems to align with the spiral arms. So we have magnetic fields, we have measured some of them in different directions. We don't know all about it. Unfortunately, it's not super well known exactly the structure of the field, but we know a lot about it. So instead of looking at cosmic rays to understand the low energy cosmic ray puzzle, we look at gamma rays. And this is one of these beautiful telescopes that are put in the ground to look at showers, just like the cosmic ray showers, but triggered by gamma rays. And you can see this is a building, so the distance between them are not that high because they're looking at lower energies. They're looking at TeV, just like the LHC and Fermilab, the same energy scale for gamma rays. And here is the smoking gun, hopefully, of cosmic ray acceleration. These are supernova remnants, and they are imaged in here in X-rays and here in gamma rays. And they seem to be showing us the sites in which these protons are being accelerated. That's totally not written in stone yet, but it's pretty close. And so the answer to the low energy cosmic ray puzzle might well be that supernova remnants, which is what Fermi expected decades ago, might be doing the trick. So supernova remnants are, the end of a star. It explodes, it gives you this huge shock, and you can see them in different phases here with the Chandra data, for example. And they might be responsible for the low energy cosmic rays. But the high energy cosmic rays are not. These kinds of objects cannot reach 10 to the 20 electron volts. So the puzzle for me continues. The puzzle at the highest energies continues. They might be able to reach 10 to a TeV or so, but there's, between a TeV and 10 to the 20, 8 orders of magnitude missing, and these guys cannot make it to 10 to the 20. So another object out there is responsible for the 10 to the 20, and we still don't know exactly what they are, but I'll tell you what we know so far. So just to remind you, charged particles in magnetic fields, they rotate, I mentioned that already, but the higher the field, the shorter the radius, the higher the energy, the larger the radius. So eventually, suppose your galaxy is this blue little arrow here. If you have a very high energy particle, it might not actually turn around very much, so you should be able to point back. And this is what this image is showing you. So you have 1 eV in our language is 10 to the 18 electron volts. So the solid lines are paths around our galaxy towards the Earth, which have of particles, protons of 10 to the 18 electron volts. And as you can see, they do come straight before they hit the galaxy, and this is the galactic plane, and then they turn around and they come, in a random way. So by the time they arrive on Earth, you don't really know where they came from. But the dotted lines are 10 eV, which is 10 to the 19, so 10 times 10 to the 18. For 10 to the 19 electron volts, they're already barely turning around. They leave the galaxy before they get turned around very much. And at 10 to the 20, they're straight lines. Okay, so at 10 to the 20, particles that arrive on Earth will be pointing exactly to the direction they came from. At 10 to the 19, they will be turned around by a few degrees, and at 10 to the 18, they will be completely messed up, so they will be isotropic. Okay? So the goal is to look at 10 to the 20 electron volt particles and just see where they came from. That will be easy. That's astronomy. The only difficult part is catching them. That's chasing the cosmic bullets part. Okay. I have a side question here for those who did more than physics or are doing it right now. I was in class today and you learned Lorentz transformations. So, again, I think one thing you will learn is that TeV is 10 to the 12, and 10 to the 8 times 10 to the 12 is what we're looking at 10 to the 20 electron volts. So on the side here, what I wrote is the proton energy is 10 to the 20 electron volts. The mass of the proton is, say, a GeV, just for today. No significant digits other than 1, and that's 10 to the 9. Okay, so the gamma factor here is 10 to the 11. Remember gamma factor from Lorentz transformations? So just for fun, a proton at these energies, in that frame, in the proton's frame, how long is the age of the universe? Okay, so by the end of the lecture, you tell me. Okay, so this is another back of the envelope fun question. Given the LHC magnets, which reach 10 TeV, 7 TeV, using 27 kilometers, how many kilometers you would have to do a circumference to reach the energy of 10 to the 20? And the answer is between Sun and Mercury. So the size of your accelerator would have to be very expensive, even by NASA standards. Okay, so that's not an option. So we really should use those particles as well as we can, because they are the particles that reach the highest energies as far as we know, and even if they're rare and difficult to detect, let's go for them. So what we decided to do in 2007 is the beginning of this era. Auger, the Pierre Observatory, was to use both the astrophysics and the particle physics that we know and try to really nail down what the origin of the highest energy cosmic rays are and what can we learn with these 10 to the 20 electron volt particles. The project began, I'll show you soon a picture of a friend of mine and Leo's, Jim Cronin at the University of Chicago, and he was able to gather 18 countries behind this idea. And these 18 countries, with now more than 400, started with 10 people, but now we have over 400 people involved. The goal is to build 2 observatories for these particles. One in the southern hemisphere, which we finished in 2008, and that's a 3,000 square kilometers one. And then we want to start as soon as the funding agencies allow us to build, the US funding agencies, the European ones already have given us a green light. We want to build in the US a 20,000 square kilometer array. Okay, so let me tell you about what we found with this group. So just to give you a sense, if you want to visit us, we are up here, close to the Great Lakes. You have to fly. The easiest way is to fly to Santiago, Chile, and then take another plane over the Andes, beautiful trip to Mendoza. Mendoza is where really good wine, Malbec, I recommend, type wine, is worth drinking. But if you do, then you stay in Mendoza and you sleep, and then the next day you drive 5 hours down, or you don't drink the wine and you can go right away, which is what I do. I drink the wine on the way back. Okay, so you go 5 hours down driving, careful, and then you reach this tiny little town called Malargüe over here, and everybody will know you. If you say you're working for the Auger project, actually many miles before you get there, people will be very nice to you because you can say Auger and they will treat you very nicely. And what we did, this huge collaboration, is fill this whole area, 3,000 square kilometers, with 1,660 particle detectors, which we call tanks, in a surface array. And then we built 4 observatories that overlook this array. Okay, so, oops, I forget that I can do that. This is Jim Cronin from the University of Chicago, and this is a beautiful building that was actually funded by the university, but it's the campus, the central campus, and all our data acquisition goes in this room, so all the computers are here, and It's a really nice campus, and here's one picture of some of us. This is me. I'm next to a big guy with bright t-shirt to make me find myself very easily. And this is just one of the groups that was there during a collaboration meeting. This is all the flags of the countries involved. So if you're not from the US, you might find your own. This is mine, by the way. I'm from Brazil. And here you see what a shower would look like in a sort of cartoonish, and here are detectors. Okay, so we have the first hybrid detector of ultra high energy cosmic rays. What do I mean by that? I mean the following. There is the easiest technique is to make a large array of detectors that will detect your particles as they hit the ground. And I put this little cartoon here in an angle so you would see that this tank gets hit the most and the other ones get fewer particles. And there's a little bit of an angle, so the timing between the different tanks is crucial to figure out the direction of that shower. This kind of detector is really nice because it works 24 hours. So unlike any other astronomy project, astronomers usually like to work at night when the moon is not out. For us, for the particle detector, that happens 24 hours, so we don't care where the moon is for this kind of technique. So we get large quantity of data. There's another way of looking at these showers, which is a little more clever in the sense that you don't directly catch the footprint of the shower, but you actually see the shower developing in the atmosphere. So your detector is really the whole atmosphere. And what they are tuned to do is look at ultraviolet light that is emitted by the particles as they interact with the nitrogen molecules of the air. So the air has lots of nitrogen molecules. These particles have the kind of energy that would excite that nitrogen fluorescence, and they fluoresce in the ultraviolet. So what you're looking for is basically a light bulb in the ultraviolet that's very faint, about 40 watts, that's moving at the speed of light. So you have to have a very fast camera, which is shown here by what we call a fly's eye, but I'll show you more pictures of it. And this is really beautiful data because you see the whole beginning, middle, and end of the shower. The problem is you can only see it at the same time as astronomers can use telescopes, in the night and when the moon is not out. So the type of data is nicer, but the quantity is much lower. So here's our particle detector, as simple as it gets. And, oops, I forgot to turn on my timer, so you tell me to shut up at some point. Okay, so this is our detector, and these are the beautiful Andes Mountains in the background, and this is a very flat region. And they are self-sustaining, totally independent units. They sit by themselves, hopefully without too much trouble from the cows in the field. And here is an image that shows one here, another one, another one, another one. So what we did was we filled this whole region, 3,000 square kilometers, with these units. And these units are separated by about a mile. It's 1.5 kilometers to be precise. And you can see, this array. And at sunset, sometimes the solar panels shine, and it's beautiful. You can see many, many of them. Here is the end game at 2008, almost the end. And here's the deployment pattern. So you will see these fans being built, which is the telescopes that overlook the array, looking at the fluorescence light. And then each of these green dots are tanks. And this is an amazing feat by Paul Manch, who's our project manager, who's at Fermilab also, to be able to actually deploy all this. And you might see that the last region to be deployed was right here in the middle, because a landowner wouldn't let us in for a long time. So you have to deal with human aspects of being able to use people's lands. But finally we did get in, and we have the complete array now. So we have all the array, all the tanks working, and this is the last tank deployed in a big party to celebrate it. And here's what the tanks look like in terms of throwing, it's a plastic tank, it's simple, there's a battery, which the cows love to scratch their backs, so we made them rounder so they wouldn't move the tank so much. There are 3 PMTs looking down, a GPS for timing. GPS you usually use to know where you are. We hopefully know where the tanks are, we just want to know what time it is when the particles come in, and that's what the GPS is for. The solar panels is all the energy we can get, because this is going to be not plugged into any electricity power grid. And we have a communications antenna that sends all the data from this tank, which is now actually a smaller antenna, to the central campus. And it's basically our detector medium is water, and the particles cross this water tank and they fluoresce. So let me show you here. So if you could, oops, did this work? Yeah. If you could see inside, you basically would see these particles making Cherenkov emission, which is the sonic version, but super light version of particles going through the water with velocities greater than light at water, they make the Cherenkov radiation, which is then captured by the 3 PMTs. Oh, I have to use 3 different. Where did they go? There you are. Yeah, okay. So here's a shower, the image of a shower that hits all these different particle detectors, and that's what we want to observe 24 hours a day. Okay, and the distances again is miles between each of these units, so it's not really to scale. But then overlooking these arrays of tanks, we have 4 of these telescopes that cover the whole area. Let's look at these telescopes in real life. This is the image of one of them, and the array is in this plane here for these 3,000 square kilometers, and this is the overlooking telescope. From the top, you can see that it has actually different regions of it. It's basically 6 telescopes that are each looking at 30 degrees, so you get 180 degrees this way and 30-degree elevation. There are 4 of these overlooking the array, so you actually be able to cover all the area of the array. And inside it looks like this. You have corrector lenses, you have a PMT camera, and mirror. So, the light comes in through this opening, it will be bouncing off this mirror and then recorded by this camera. Now, you might have heard about CCD cameras, most of you have them probably in your cell phones. CCDs, they sit there and they take photons that hit the same place for a while. This needs to record something very fast, it's moving at the speed of light, so PMTs are our option, and this is 1.5 degree pixel in the sky. Let me show you one more of these videos. So we can go in and look at this thing as if we were visiting. So at night we opened this. One graduate student from Germany opened during the day, and we haven't seen him since. It basically melted the camera, because these are very sensitive equipment for light, and it's tuned to see 40-watt light bulb at many tens of kilometers away. So it's pretty cool. And the next. So here it's inside. And these are the cameras and the mirrors, and what you will see is, from a perspective, the light coming through. So, okay. So here's a real event. This happened in 2007, and it hit right the middle of the array before the whole array was finished, and it was seen by all the 4 eyes. So it's a 4-fold hybrid event at 10 to the 19 electron volts, which is pretty cool. So these things really happen. It's not just the simulations, but the simulations are easier to show. And obviously the answer that you want to get is, where did they come from? So here is, if we can see with all these different telescopes and with the ground array, we should be able to know the direction, the energy, and hopefully the charge of these things. And then we should be able to correlate. So what we did in 2007, there was a big splash in Science magazine, we were a cover of Science, because we found that for the first 27 events that we detected above an energy of 5 times 10 to the 19, they all seem to point to active galaxies. So we thought maybe we are actually solving the puzzle. Let me show you what that data looks like. So here's a map of the sky, and we only look in the southern hemisphere, and this is in ecliptic coordinates, so the stuff on top we don't see. And in blue are active galaxies within about 100 megaparsecs from us. 300,000 million light years. And in red is our data. And what we found is that more often than not, they would actually hit some of these blue regions, more often than they wouldn't. Here is one that doesn't. And in particular, Centaurus A is the closest active galaxy, and it seems to have lots of data around Centaur. And that's still true, as I'll show you in the new data. But with this data alone, we decided to go public, because we did a sort of fun statistics test of making a first sample with 10 events and then added to them. And if you were into statistics, as I sat through a class today, we got a 2 sigma result roughly. But we thought it was interesting enough that we should let the world know. And then after these, the evidence got to be a little weaker. Still, I put preliminary, so if somebody gets this, it won't. No, we haven't published the data yet, so this is data that is not out. And in blue, here we inverted, in blue is the AGN, and in black is our data. And we still have a huge correlation in the following sense. Our black points, our data, seem to want to be in the regions where there are blue things. For example, where I wrote preliminary, there's no data of ours, and there's very few AGN. The problem is AGN trace the matter distribution. So if it's AGN or if it's just galaxies, normal galaxies, we can't tell. Okay? At this point, we don't have enough data to test a different hypothesis. So if every single black dot came from a blue region, we would say, well, it does look like AGN are the sources. But AGN also trace what we call the large-scale structure around us, which is what this huge wall, for example, looks like here. And this large-scale structure has lots of galaxies. For every single AGN, there's 10 normal galaxies around. So if the data came from, for example, gamma ray bursts, explosions in normal galaxies, they would have a similar distribution. And so to test the two hypotheses, we need a lot more dots than the ones we have so far. Okay, so it's just the beginning, and we can't really tell that it is AGN. Definitely. But the first 27 events were a little more hitting the target than we expected. That's why we thought we'd let the world know what's going on. But now we know that, for example, one of the things that you will see here is that in this plane, which is the galactic plane, the coordinates of this image and the other one are different. So the galactic plane is here and this part, which is where the first images I showed you of the galaxy would sit. So the galactic plane, we don't expect correlations to happen, and you see a lot of black dots that don't hit any blue, mostly because you can't see AGN behind the galactic plane. You have all kinds of problems with the optical. So the catalog of AGN is not a perfect one to begin with also. So we have all kinds of issues to solve, but it does make a lot of sense to be from AGN. So let me show you what an AGN looks like. AGN stands for active galactic nuclei. And what we see is the nuclei of galaxies, which have these huge jets coming out of them. So here's a composite image of Centaurus A, which is the one that, if you remember here, we got a lot of events around it. So it does look reasonable, but we can't prove it at this point. And here are the images in different wavelengths. So remember in the beginning, I was talking about different photons that we use and how Galileo really liked optical, because that's the easiest one for us all to relate to, because that's our eyes. With our eyes, Cen looks not very, very effective as a galaxy. You see there's an obscuration thing here, and it has sort of a white halo, but you don't see any jets. It could be a totally calm galaxy. But if you look in the radio, you don't see this part, you don't see this white, and you just see these two jets coming out of the nucleus of it. So in radio is a totally different image of the exact same object. And then in X-ray, you have both a little bit of the structure of the optical, and you also have the jets coming out. So here's a composite of all of these. And what we think is happening in active galaxies is that you have a supermassive black hole in the center of the galaxy that is gobbling up as much mass as it can, and somehow, because of the dynamics of the disk that's feeding it, it is able to make these incredibly stable jets coming out of it. Something to do with how the magnetic fields realign when you get swallowed by the plasma around the black hole. And it's not a trivial problem to solve, but the basic concepts are around. So they are certainly nature's strongest accelerators as far as other wavelengths we've known so far. So the bottom line is that we don't know for sure, but it does look like our data is preferring these regions. And it would make some sense because, and so one thing you can learn is that they're not in our galaxy. So these accelerators that reach 10 to the 20 electron volts are really extragalactic. That for sure, because the distribution that we see of the black dots does not follow that plane. They're not all lining up in this plane, so they're definitely not coming from the galaxy. So they are coming from this large-scale structure around us. Are they coming from AGN or are they coming from gamma ray bursts? It's still to be determined. But here's what, some of our conceptions of what's going on with these jets. So we know these jets are very, very collimated, and they're very stable, they're huge. And somehow that has to relate to the fact that there's these supermassive black holes in the center of these objects that have to interact with a lot of plasma. Okay, so to finish up, I want to talk to you about the future. So what next? We are, I think, at this point, with the results that we had in 2007 and what we have so far in 2010, just at the tip of the iceberg. We have very few events. This is the image that I can show you today. This has about 60 events in black, and it's going to be very slow. We get about 24 events a year, 2 a month. So it's going to take decades and decades to get to hundreds of events. So So I'm going to be very much more than retired by the time we get an answer. So what we would like to do is get a lot more than 2 events a month and be able to really know what's going on. And to do that, the easiest way is to make a much bigger array. So here is what we will have in 10 years. In red is what the AGN distribution looks like, and in black is the data that we expect from Auger South. And Auger North, which is much bigger in the design, would be able to really map out these structures very precisely, so we would be able to tell the difference between AGN and other possibilities. So if you want an analogy, at 3,000 square kilometers, what we built in Argentina is roughly Rhode Island. What we want to build next is Massachusetts, which would be 8,000 square miles or 20,000 square kilometers. And we don't want to do it in Massachusetts. We want to do it in Colorado. The difference that we're going to, so, this is 7 times the area, but we're not going to go to the funding agencies and ask for 7 times the money. It's actually just twice the money because we're making the distance between the tanks much, much wider. Instead of 1.5 kilometers, it's about 1.4 miles, okay, square root of 2 miles. This is what it would look like if we did it in Illinois. So we would go from Chicago all the way to Bloomington with the array. But we're actually doing it in we want to do it in southeast Colorado and probably Kansas. Kansas is getting involved. We started an R&D there, so research and development. We're already doing a few sort of probes of the communication system, which will be different. Here's the layout of the land. We have grazing here and a lot of farm on this side. And the farming people are very much interested in having this happen. The state of Colorado is helping with tax breaks and so forth. And here's what the design of the fluorescence telescopes would look like, so that it would cover the array just like in the south. So the only difference is instead of having, so here's a mile grid. The west was divided up in mile grid in an array of square mile land. So each farmer basically has one of these. So each of these tanks would have at least 2 farmers or 4 that you can talk to. And the idea would be to put one tank here and another one across, so the square root of 2 mile grid. Because we actually in the beginning, before we got Auger South going, we thought of doing a mile square grid. And because we want to do a lot more area for a similar price, we decided to go this way so that we can cover much more area. And what we're giving up is basically coverage of the low energy cosmic rays, which we have in the south, so we don't lose much. Another technique, the Japanese are developing what's called the Japanese Experiment Module, JAM, USO, which is Extreme Universe Space Observatory. And their idea is to put a fluorescence telescope up in the International Space Station. And that was planned for 2013. It might actually slip to 2015. But it would be quite nice. They can see with one telescope a much, much larger region. The energy threshold is a bit high, so they won't see too many events, but it will be a very interesting sort of what's happening way above 10 to the 20 electron volts. So that's an alternative technique. And people have planned for free flyers, because in principle there are 5 million of these ultra-high energy cosmic rays that one should be able to see. But it's quite tough to do it by covering the whole land with detectors. So what we expect Auger North to be is sort of the last resort as far as making it a big array, and then we would then try to go to the space to look at more of them. But that's definitely more expensive. So to summarize, I hope I convinced you that the Pierre Auger project is an interesting one. We have built the south, we want to build the north. The goals are to discover the origin of ultra-high energy cosmic rays. Where do they come from? What are these cosmic objects? But we also want to understand the interactions at these highest energies. And for the interactions, one of the things I did not cover, because I didn't think I had enough time, was the neutrinos. Because these cosmic rays, because they have interactions with the microwave background, they will produce a lot of neutrinos, and we should be able to detect neutrinos with the exact same telescope. So we would like to do charged particle astronomy in the sense of knowing where the cosmic rays come from, but also understand interactions using these high energy neutrinos. So I think it's just the beginning, and we should be having a lot of fun. So thank you.
How long does it take a student to get through and write a PhD?
My students, about 4 years, 4 and 5. We had, yeah, it's not too bad. There's lots of questions to be answered.
Questions?
Does anybody know the answer to the question here? So for a proton at 10 to the, you do, oh, but you don't count. For a proton of 10 to the 20, the age of the universe, I guess I didn't give you one number, which is the age of the universe, but hopefully you know that roughly.
I couldn't really do it without a calculator. I don't have a calculator, but it's something extremely small.
Anybody else? It's, yeah?
I have a question. In the future, do you think that these charged particles could be harnessed in some way?
To do something like get some energy out of them?
Yeah.
Yeah, I think the low energy cosmic rays might be useful. I have no idea how to do it. The ones I'm interested in are too rare to be of any use, except for fundamental physics. But I could imagine the lower energy ones people have. Well, you know, one thing you need to deal with them anyway, right? If you want to go to Mars and you're not a robot, you're going to run into a lot of this stuff. So you need to know what to do with them.
How much money does it cost to build one of the detectors?
How much time it takes?
How much money does it cost?
Oh, the money for the whole project, it was $50 million, which if you've heard of, other budgets, it's pretty low.
So how much did it cost per tank?
So 50 million divided, well, take, let's say, half of it and divide by 1,660. Because the other half is the fluorescence telescopes. They are 4, but they're more expensive, so half and half is good. Yep.
Can these high energy particles be dangerous?
That's a good question. I've done so the low energy ones are definitely dangerous in the sense that they, for astronauts out there, they do get serious muscle weakness due to the radiation that they go through when they're up in space. So it's not a fun. I mean, the Earth is a nice blanket to live under. Now these highest energy ones, they have a lot more energy, therefore they could do more damage, but they don't stop very fast. So they pretty much go through your body if they come this way. If they came this way, they might come, you might want to estimate what they would do. So a little bit of damage, but you wouldn't notice. If you could stop it all in your hand, then it would be like a tennis ball serve. It's about a joule. But usually it goes right through, so you don't quite feel it. Tens of joules.
Are those particle showers, are they visible or are they invisible?
They are visible in the ultraviolet. So if you have ultraviolet eyes, then you should be able to see them. I guess the Superman has X-ray eyes, right? Which I don't know what that means, but anyway. So they're not visible in the other sense, in optical sense.
So you said that you do using some accuracy with going to the virus basically between the tanks. Is this accuracy that you're losing basically negligible or?
Yeah, so he's asking, we get just a sample of the shower. We don't get all the particles. We get one here and 1.5 kilometers away. And for the energies that we're interested in, we want at least 5 tanks to give us some data. So then we can make a profile very nicely. Now, if you were interested in lower energy ones, they will go right through the tanks. So that's why I said when we put in the north much bigger distance between the tanks, we will not look at 10 to the 18 electron volts. We will only see above 10 to the 19. But if you're interested in, if you can make particle detectors right here by having meters apart, and then you have a lower energy, because basically you have a combination of the energy. The higher the energy, the bigger the distance you can reach. But the rarer they are, and it goes like the energy cubed. So if you put short distances, you will get lots of the low energy ones, very few of the high energy ones. So you're better off making it very, very far apart if you want the highest energy ones.
Sorry, I know that for these 2D, a lot of times we're considering we're making a veto shield to protect the detector against muons from cosmic rays. But I don't know about the other detectors. Do you know if at CDF and P0, do they have actual cosmic ray veto shields, I guess?
Actually, they all see cosmic rays a lot. Depending on what you want to do, for example, if you're looking for dark matter, then you really want to be very, very deep underground to get rid of as much cosmic rays as possible.
But particle detectors, they are actually, before the LHC actually got going, both Atlas and CMS were using cosmic rays to check their equipment. So they're actually pretty happy that there's this, particles coming through, so they can actually check what's going on. So it's not so problematic because they know exactly when their interactions happen. I mean, there will be some cosmic ray contamination, but that's not their main problem. But for dark matter, that's a main problem because you want this very rare event that's going to give you a tiny little bit of energy, so cosmic rays would totally overwhelm you. So that's where you go underground very deep. Or if you want to look at photon decay, so some things that you want very small signal, you want to hide from them, but not everything.
Well, let's thank Angela for this.